Welcome to Group 1's rocket design video, including Thomas, Daisy, Michael, Jamie, Yuya and Jabir. Our objective is to design a streamlined air-water rocket that will successfully ascend and safely descend, but also stay airborne for the longest, and the other objective for our payload not to be harmed throughout flight. Impulse is the change in momentum of an object, but for a water rocket, impulse is the integral of thrust multiplied by the change in time.
Pumping air into the bottle, you increase the pressure inside, which then increases the potential energy of the compressed air. Upon launch, the air forces its way out of the nozzle, pushing the water out with it. The higher mass and density of the water gives it a significant amount of momentum, producing a large impulse. The thrust produced depends on the water fraction. The more air space allows for more potential energy, but the more water increases the mass, leading to a greater impulse. The optimal fraction for thrust is typically between 0.5 to 0.7.
The rocket must have directional stability, meaning that when a force interrupts its straight path, it is able to return to a straight path, although not always in the same direction. As the fin's size increases, so does drag. If the fins are too big, there will be too much drag, so it is important to keep them at a reasonable size. The fins should be placed at the rocket's base to maximize the distance between the center of mass and the center of pressure, where all the aerodynamic forces act, as this increases stability.
Mental part of the rocket tasked with the slow descent to both increase the time of flight and reduce the impact velocity and hence magnitude of deceleration to prevent the egg payload from breaking. As you would imagine, a larger parachute will cause a slower descent speed. This is due to the larger area increasing air resistance and hence producing a larger resistive force to the rocket's descent. This larger resistive force will create a smaller terminal velocity, causing an overall longer time of flight. However, there are issues that come with the use of a large parachute, such as the weight, space taken up within the rocket, and the difficulties with getting it to open and not tangle. This hence leads to an optimal size of the parachute.
The first design decision involved the placement of the fins on the rocket. While initial ideas considered adding cornerstone fins near the top, research showed that placing the fins as far away from the tip as possible shifts the center of pressure behind the center of mass, aiding in flight stability. CFD testing also revealed that fins closer to the top increased drag, affecting airflow. Similarly, for the nose, a tangential guide shape was found optimal based on the bottle and payload specifications through CFD analysis. Ideal calculations determined the best water-to-air ratio at 0.8, which was integrated into the final launch setup. However, Unity simulations showed that build quality significantly impacted launch success. To ensure precision, CAD and CAM software will be used.
Lesson number 1. Aerodynamics and stability. By analysing different fin shapes and sizes, we're able to determine the most efficient fin design. Lesson number 2. In order for the rocket to take flight, we learned how to apply the concept of thrust generation. The CAD software allowed us to precisely cut components onto our rocket. This, combined with the ability to run simulations, allowed us to make accurate predictions on how our CAD parts will perform without having to make numerous prototypes.